Okay, I guess I'm starting. Just to make sure that all of you guys are in the and um, as far as I understand the topic exam is from current to PHYS. So let me start with if we have a conductor and there is a potential difference between 2 points in the conductor, there will be, because it's a conductor, there will be 3 electrons, 3 charged particles, and they will flow from one end to the other, from high potential to low, high potential to low. So that is basically what's the reason why the reason we have conductors. So the current is, if you have a constant rate of charge flowing through a wire, you can write current as that. And if the rate is varying, you can write it as so. And there we have, well, um, there are 2 kinds of charged particles that we know of, positive and negative. If you apply a potential difference in a conductor, positive charged particles always flow from higher potential to lower potential. Flows in the opposite direction. And we have decided that scientific community as a whole decided that let's make the direction of positive charge to be positive current. So we just follow that convention. It's just easy for all of us. So the direction of current is basically defined as flow of positive charge. The direction of flow of positive charge. So in a conductor, when charged particles flow, there is always resistance against that flow. These charged particles hit each other and they slow down. Because there is potential difference, they'll start flowing again. So this whole process is because there is this property of material called resistance. So a conductor having resistance of a conductor can be defined with this formula. Not a conductor, but in general, any metal. And this is called resistivity, which is constant for a material. So it doesn't matter what shape it is in, it's always constant, but resistance varies from the shape of the material. Because of the shape of the material, different materials have different resistance values based on what the length of that material or wire is and surface area of the wire. So if the length is more, there will be more collisions between charged particles when they travel. So you have more resistance against its movement. That's why we have more resistance for a long wire. And for a bigger area, in the same way you have for a bigger area, you have more resistance for a wire. If you have 2 resistors in that, the effective resistance of that wire is just sum of those resistances. Let me call it R effective, R1 plus R2. So this, you can make sense of this because like I said, the more length of wire you have, the more resistance it offers to the flow of charges. So more length of wire, so it's like two different wires, two different resistances. So you add up, you will have more resistance against flow of charge. So that's for series. For parallel, we have, so parallel is when two wires are like that. So they basically have same voltage across them. So voltage across these 2 points, this potential difference and this potential difference will be same. Always make sure that when you have two resistances and when you think they are parallel, there shouldn't be any other resistance coming in the middle. If there is another resistance that comes in the middle, they are not parallel anymore. Let's say you have something like this. Like this. These two wires are not parallel anymore because you have another resistance in the middle. So the voltage across these 2 points are not same. Some voltage is being used by this resistance. And because there is another wire coming out, there is current flowing this way, that way, all the different ways, and they cannot be counted to be in parallel. So you have to use some kind of manipulation to find out resistance and stuff. Speaking of manipulation and doing problems, let me talk about Kirchhoff's two laws. One of them is called Kirchhoff's current law. Let me just write KCL. It's also called KCL, Kirchhoff's current law. Sometimes it's also called junction law. So what the law says is that if you have a junction and you have some currents coming out and some going in, sum of all currents coming in will be equal to sum of all currents going out at a particular junction. So you can understand it because charge goes nowhere, right? All of the charge that comes into the junction has to go somewhere, and that goes through one of those wires that takes current out. So in this case, I1 is going in, I2 is going in, that's it. So sum of currents going in sum of I in is I1 plus I2, and all the remaining currents are going out. So let me just write that as I out. That is I3 plus I4 plus I5. So Kirchhoff's current law says this should be equal to that. So I can write it as I1 plus I2 is equal to I3 plus I4 plus I5. Next is Kirchhoff's voltage law, or KVL, or loop. You can call it whatever you want. So this law states that if you have a loop, a closed loop, total voltages and total potentials, sum of total voltage and potentials should be equal to 0. So you have to be careful when you're doing this, because you have to take into account positive voltage and negative voltage. So you have voltage drop, which is negative voltage potential, or you have voltage increase in voltage, which can be called as voltage gain. So if you have a battery like this, let's say I have a resistance, like this. If I want to do Kirchhoff voltage law for this, I will have to pick a direction for my current, and I will have to pick up a direction for me to go around the loop. So let me just pick the direction like this. Let me call that I1, and because there is no other branches going out anywhere, all the current going in has to go out from here to here. So this will also be I1. And if I of this E, and I pick my direction of my travel to be this. So let me start at this point. So from here, I pass the voltage, and because I go from lower potential to higher potential, there is a gain in voltage. So that is positive. E. And if you have a resistor and of current in the resistor and your direction, the direction of the travel that we choose to go in the loop are same, you have to consider that as a drop in potential. So like I said, drop in potential is always negative, so that will be I1, and let me call that R1, R2. So that will be I1 R1, and for this one, because current is going in this direction in R1, it has to go from here to here, so it's in that direction, and my loop is also in that direction. I have taken my loop, so that will be minus I2 R2 is equal to 0. So that's how we do KVL. For this is a simple circuit, so that's how we do KVL. So let me choose a problem. V1, V2. So whenever you are given a battery, uh, the plate with bigger size is usually positive potential. So just to let you know. So this is a battery, right? That's a voltage source. So if you are given a battery like that, this is always the positive potential, and that's negative. So when you go in this direction, it will be a voltage gain. If you go in this direction, it will be a drop. So for a circuit like this, we have to write KVLs, 3 or 4 KVLs, and then solve for them. Okay. Let me just write on the light. So that's the question. It's pretty self-explanatory. So in this question, they have given direction of I1 and I3 as indicated here, but it doesn't have to be like that always. You have to. Sometimes you will have to do it yourself. Just pick a direction, go with the direction. If you get a negative value, it means the direction that you have chosen is not. I mean, it's not that it's not correct, but the current is flowing in the direction opposite to the one you have chosen.
Can you explain the remember the last example showed the clockwise rotation? Can you explain it?
Oh, this one.
Yeah, like I think that.
Okay, so let me just take this part of the loop. That's the resistor R1, and the current flowing through that is I1. And like I said, I have to choose the direction of my travel. So let me call, because it's a clockwise direction. At that point, it'll be in that direction, right? This is going in that way. So whenever these two are in same direction, the direction of current flow and direction of your travel, then you have to take it as a negative. That's a drop. So what's happening here is some of the voltage some of the voltage of the battery is being used by the resistor to basically heats up, but it is being used by a resistor. The same thing is happening here too. Okay. So in this case, for writing Kirchhoff voltage law, we have to pick loops separately. So we can make several loops from this example. Let me just start with this one. So if I do it separately, that's how it looks like. That's V2, R5, R4. Always keep in mind that there are other branches coming out from here. So the current going here doesn't necessarily have to be the one coming out. So you will have a different current there too. So let me just write this as I5. And because here there is no other branch coming out like this, it's not connected to anything else, this current flowing in has to be coming here, right? So that's also I5. And let me pick a direction, like I said, I'm choosing clockwise again. In that case, I'll start here at this point, and because this is a negative terminal, that is a positive terminal, when I go negative to positive terminal of a battery of a voltage source, there will be a gain in the voltage. So that's a positive value. So V2, um, that's V2, and here you have resistor R5 current going downwards, and the direction I've chosen is also coming downwards at that point. So like they are in same direction, take it as a negative. So that will be minus I5 R5. Oh, just to let you know if you are not aware, for a resistor, voltage is given by I times current times the resistance, and for R4, direction of current, because it's going here downwards, will have to go in the onto my left side, and that's the same as the direction of uh, direction I've chosen. So both of them are in the same direction again, and that's a negative again. So that's one equation. I got one equation from that. Oh, it's actually the same. I'm erasing this. Let me pick another loop. So now let me pick this loop. So I already told picked a value here. So make sure that you are consistent with what you have done in the in the whole problem. So because I said that's I5, I'm going to stick with that. Now in this, well, I don't have to take this into account. Just as long as it completes a loop, that I should be good. So that's how my loop looks like. Now we know current through all the resistors, direction of current through all the resistors, but except for R6. So let me write that as I6, and this was I5. Because there was another connection coming up, I5 cannot be to I6. Now let me write the KVL for this. So let me start here, and the direction I choose is clockwise again. So from here to here, there is a gain in voltage, so I'll call that V1. And here, the current in resistor is that direction, and I am going clockwise, which is that direction, which are opposite to each other. So it will be plus I2 R2, and at this point both of them are at this resistor, both of them are same direction, so that's minus I5 R5, and here it's minus I5 R4, and here the direction I have chosen is that way and the current direction is this way, so that's positive I6 R6, that's it, equals 0. Oh, uh, direction is that. So this is going down and we are going this way, so that's uh, that both of them are in opposite directions to each other, so that will be positive. That's another equation that I can use. Now we know the current going through this resistor R1, and that's a current that will come out here, and because I have chosen I6 to be that way, I'll use Kirchhoff current law here at that junction. So currents, let me draw this junction. At that point there is I1 coming in, I3 coming in, I6 I've chosen this direction, so that's going out. So sum of currents coming in, going out should be equal. So I1 plus I3 is equal to I6. That's another equation. So we have four unknowns and three equations. So we will need an application to write it down. So at that junction, I said for Kirchhoff current law, currents going in has to be equal to current coming out, right? So in this case, it was I1 plus I2, which were coming in, equal to I3 plus I4 plus I5. So the same way, we have okay, in this example, we have I3 coming in to that junction, I1 also coming into that junction, and I6 going out. So we have that equation. Oh, I can also write KCL at that junction. I2, I3, I1. So at that at this junction, current coming in is I2, and currents going out are I1 and I3. Um, yeah, I'm So in general, with mathematical equations, the number of unknowns you have, I mean, the number of equations you need is usually equal to the number of unknowns you have. It's just counting if I have enough equations. Yeah, like you said, I'll have to use another loop. So I'm not going to draw it again. I'll just do it here. So I'll choose this as my direction, and I'll start at this point. Here I'm going this way and current is going out, so that's plus I1 R1. I don't have to write plus. And then at this point, the current is going that way and I'm going that way. So that's I3 R3. And for this battery or voltage source, I am going from positive to negative. If we go from negative to positive, it's a gain. If I go from positive to negative, that's a drop. So minus V1, drop is always minus, equals 0. Okay. I can change this equation in terms of I1, just I1 and I2, and then I can use that equation with this to simplify. Okay, so from these two equations, I1 plus I3 equal to I6, I1 plus I3 equal to I2. So I can just I2 equal to I6. So if I just substitute that in this equation, I can write this as 6, sorry, I2. I2 R6. I just use this and substitute it in that equation. And I can write I3 in terms of I1 and I2 minus I1. So I1 R1, I3 is I2 minus I1 from this. So I2 minus I1 times R3 minus B is equal to 0. This equation turns to that. So now I1, I2.
Get rid of R so altogether. It equals R2. So if you just cancel out R2, you know, IG equals
oh yeah,
I6.
I haven't seen that.
Then
Oh no, wait.
yeah, keep that one, get rid of the R6, and just solve for I2, or substitute
Sure.
I2 for I6, or vice versa.
We can just write that as 2I2 R2, right?
Right.
No, wait. R6 is
It's the same.
the same. Okay. So I can write that. Of this. Oh, we also had some other. R1 is equal to R5. It doesn't matter. So I have 1, 2, 3, 4 of them. Okay. So from these two equations, I can subtract this from that and get rid of this one of these with this one, and sorry, this one. Let me just write it down. Can someone tell me this?
And minus I4 R4.
I4 or
Yeah,
I5?
minus I4 R4 equals 0.
I4 is equal to I5, right? I
Yeah.
just checked.
Okay.
What was the other, the longer one? V1 plus. I'll just write that as I2 R2. And so if I subtract this that, I can get rid of this with this and this with that. So I get V1 minus V2 because I subtracted this equation. It's a minus. R2 is equal to 0. V2 or I3, but we equation which relates I2 to I3. I can just change the size can be charged to is equal to time is just from 0 to, let me call it t final or t finite, whatever you want. So that would be t over r1 from 0 to t. So now EC when I EC minus Q0 plus ln of EC is equal to T over R1. If I make substitution, that's what I get. And once I get that, I can solve the equation. EC minus e to the minus t over r. Did I do something wrong? If I multiply c to the other sides. So yeah, if I make this solve it. So that's what we get. With EC is the so E times C is basically maximum charge that the capacitor can store. So Q is equal to Q max in, multiplied by 1 minus e to the minus t over RC. So what this equation says is that, wait, yeah. So at time t equals 0, e to the 0 will be 1, right? So at that point you will have charge in the stored in the capacitor to be equal to EC times 1 minus 1, which is 0. So as long as you close the switch, there's no current, there's no charge stored in the capacitor. After a long time, which we take as t to be infinite, we write, we get Q, charge stored in the capacitor, is equal to EC times 1 minus e to the minus infinite is 1 over e to the infinite, right? That's 1 over infinite, that's 0. So you get charge stored in the capacitor to be the voltage of the battery times the capacitance of the capacitor. So it makes sense because when you just close the switch, there's no charge stored on the capacitor plate. Gradually, because a charge flows from the positive plate to this plate, and from the negative plate, negative charge flows to this plate, you have charge slowly accumulating, and after a long time, there's no current flowing anymore, and you will have that amount of charge stored on the plates. Similarly, if you have charged it for a long time, and let's say you have then connected it like this, so you get rid of the battery, you just have this circuit now. Then what happens is this capacitor, because there is a lot of charge stored on the capacitor plates, when you let me avoid this. So you charge the capacitor for a long time and then connect it to the resistor. So because you have charge like that, you have current flowing through the, so this basically acts like a battery. Current flows through the resistor, and the charge in that case can be written, charge as a function of time is EC times E exponential of minus over RC. So at time t equal to 0, maximum charge flows, maximum current flows, but time goes on, you will have no charge flowing because all the charge has gone from this plate to that plate, or vice versa. We know for a capacitor, voltage is given by Q over C. So voltage as a function of time can also be written in this way. Just voltage can be written as E times exponential of minus Q over RC. So this is the voltage stored in the capacitor. As maximum voltage will be stored at time t equals 0, just as you close it. But as time goes on, voltage will decrease because the charge has decreased. So at the end, after a long time, you have no voltage across these two capacitors. All the charge was discharged. Do you have any questions? Any? Not just this part, but in general in RC circuits.
This is in relation to RC circuits, so I was wondering if I can explain how we know how the resistors are connected in the grid, so I know this is that. But sometimes I feel like, okay,
Let me do that quickly. Sir? Oh, I'm sorry. So this is, I am not going to solve the whole problem.
no,
I
just explain
yeah.
how we know it's so.
So think of this as a bunch of wires that you have, which has resistance. So I can just pull this wire to the other side and simply write like wire as being this way, right? There's nothing else coming out of that wire. So I just take that whole wire and just, for sake of simplicity. The same way, I can take this.
Wait, I wasn't drawn before.
Sorry?
How would that wire on the right drawn before?
Oh, it was drawn like this. So
We just did that. Like,
this one.
maybe the one of that was,
Oh,
then that we, yeah, that.
oh, good. Oh, thanks. Yeah. So and for these two resistors, similarly, I change that for sake of my convenience. So that was R2. That's R1. So there are no resistors that are coming out of this particular place in the wire. I mean, you can just take them to be in series like that. And this, I can take that. Okay. So this looks way better than what that circuit looks, right? So now these two are in series. I add them up, R2 plus R, and then I can change that to this is R2 plus R3 because those two are in series. That's R5. That was R6. That is R1. So now these two are in parallel, right? Oh, okay. So these two I can,
Those are in
yeah,
series.
those two are in series. R4 plus R5. Now these two are in parallel. So you can take 1 over R2 plus R3 plus 1 over, and that will then become, that will then look like this, R1, R6, and this is R effective of those two parallel circuits. So I can, that's the,
They're all in series.
they're all in series. So just draw it in a understandable way that should be, that should be, it's not that hard. So, okay. Magnetic field. So yeah, any current carrying conductor or any, yeah, any charge particle, if it travels, it has it gives out some, produces some magnetic field around it, uh, and this field, the direction of this field can be taken to uh, can be obtained by using right hand rule. So if you have a wire and you have current flowing through that wire, you can take point your thumb toward in the direction of current, which is that, and curl your fingers. Always use your right hand. If you use your left hand, that's wrong. You'll give the opposite result. So current going in that direction and curl your fingers. The direction of your fingers. So you'll always form a circle. Magnetic field always is in complete loops. So in this case, I have current flowing like this. So the current, magnetic field is like that. So you have magnetic field like this around this wire. So if I have, let's say, a circuit like this, current was flowing like that in the circuit. Now I'll point my thumb along the direction of current and then curl my fingers like this. So in the inside, magnetic field will be into the page like this. In the outside, at this point, let's say, it will be coming out of it. So that's it.
PHYS law.
Okay. So if you have a current carrying conductor, to find out the magnetic field because of that current in that conductor, there is a formula. So let's say you have a conductor like that and you want to calculate the magnetic field at this point because of this small element in the wire. You can use that formula to calculate this magnetic field at that point. These three are constant. I mean, this is a constant value. I is the current flowing in that wire. ds is the length of that small element, so that will be ds. And you will have to take the direction. So in this case, IDS is that way, and R is the vector pointing towards the point where you want to calculate the magnetic field. So IDS is pointing this way, and you are taking cross product of IDS with R, vector R, and R is that the magnitude of the distance from that point to this point. So if you have a wire like that and you want to calculate magnetic field at that point on a wire, the current is going this way, which is along, let me take that as positive x-axis, along x-axis, and the R is also pointed that way. So when I take cross product, the angle, so I have IDS, because it's a cross product, I take IDS times R times sine of angle between IDS and R, which is 0. So what this says is you don't have any magnetic field on the wire because IDS and R are parallel to each other. Do you want me to do a problem based also? Sorry? Let me do it for circular loop or circular element, or if you have one in your mind, you can do allocation, or I can do whatever I do.
Okay, let's see something 26 minutes out. Just show them.
No, I just thought I'd do for a loop, a semicircular, or an arc, or I don't know, an infinite wire. Anything. If you have a question that would be better. Okay, that's okay. Sure. So this question says a rectangular loop of wire with sides. Well, the dimensions are given. Carries current I2, and infinite straight wire located at a distance is given from the segment. You have to calculate the force on one wire due to another wire. So let me do this, but I'll do this after explaining force. a robot force. Okay, I can do that later. So let me explain Ampere's law first. So we have seen Gauss's law in electrostatics, which said if you have some charge distribution and you take let's say a shell, the magnetic field coming out of that shell, out of that charged particle can be obtained using the total charge which is located inside that shell. Ampere's law says if you have, let's say, a wire and you want to calculate the magnetic field on a loop around it. So if you have a wire and you put a loop around it, you want to calculate the magnetic field in that loop. You can use this formula equal to mu naught I. So current is I. So B is the magnetic field in the loop, and S is the length of that small element that you're considering, and you integrate over the whole element, which will give you the whole loop, is equal to mu naught I. So in Gauss's law, we had all the charge located inside to give us the magnetic electric field. In this case, we have all the current passing through a loop give us the magnetic field in that loop. A loop. So if you have an infinite wire, a simple example. If you have an infinite wire, let me write down Ampere's law for an infinite wire, which will be ds. Because it's an infinite wire, I'll just take the current I, and dot product for this infinite wire. I'm going to take the loop to be circular, and we know that for a wire like that, we can see the direction of magnetic field along all the points on that loop. So if I point my finger along the current and curl. Point my thumb and curl my fingers, I'll get the direction, which is like that. So at each and every point, it's tangential to that loop. That's how your magnetic field on that loop looks like. So, and ds in this case is the small element that we are considering, and we integrate over the whole loop. So E and ds are in same direction at every point, right? Every point we consider on that loop will have both of them to be pointed in the same direction. So the angle between magnetic field and that small element will be 0, and we know that cosine b dot ds is cosine b times ds times cosine of angle between them. Cosine of 0 is 1. So I can write this as b integral b ds equal to mu naught I. But because this is circular loop, the magnetic field at every point will be same because of the symmetry. It's an infinite wire and it should be symmetric along a circle around it. And this being the center of that circular loop. So I can take b out of the integral. 2 pi r is equal to mu naught I. So from this I can write magnetic field at all the points on the loop will be mu naught I over 2 pi r. You can use Ampere's law anywhere, but it's easy to solve only in symmetric cases. So in this case, you have because the line is going through the center of that loop that you're considering, is symmetric. It is basically radially symmetric. So it's easier to do it. But if you choose, I don't know, another loop which is like that, Ampere law still applies, but it's not easy to solve this problem because you have the dot product have different angles, different values at each of the points, and magnetic field is not always same at all the points.
So was the magnetic field the same because it's circular, or is it because it's
Circular. It's because it's circular and the wire is going through the center of that. So if it's going at some point like this, close to one of the ends, it will not be symmetric with respect to that loop. Okay. Any questions on this topic in general?
PHYS.
Yes.
Material movement time.
It's just a notation. All you have to keep in your mind is you are going along that loop, right? So it's just an element of. So it doesn't matter if you take it as dr or dp or dq, whatever. It as long as it works for you, and you'll get the answer. Should get the answer. Okay. So that's magnetism because of current carrying wire or moving charge particles. Now let's discuss force on a because of magnetism, force on a moving charge particle. So if a charge particle is moving in a magnetic field, there will be a force that this magnetic field applies on the charge particle. So let's say there is a magnetic field like this, and if a proton travels in this direction, proton has a positive charge and it's traveling that, and if you want to calculate what's the magnetic field, the force due to that magnetic field, you can use right hand rule. So what right hand rule says is that so if you, there are a couple of rules. So you can take this, you can use this rule, which is point your fingers. So this is the direction of velocity. Velocity is that direction, and is that direction. And if I want to calculate the force, I point my fingers in the direction of velocity and curl it in the direction of magnetic field. So I curl it like this, and the direction that my thumb shows is the direction of the force on that charged particle due to magnetic field. Or I can also use another rule. I can point my index and my middle finger in the direction of magnetic field, and my thumb will show the direction of the force on that particle. If you really don't remember that, you can try this. Have a look. So yeah, that's make sure that that's for a positive charged particle, positively charged particle. For a negatively charged particle, use the same rule with your right hand, and then opposite of the direction will be your force. Or you can use your left hand. People might confuse left for positive or right. So usually it's always easy to remember doing right hand for positive charge particle, and it works either way. Doesn't matter. So if you are, let's say, given the direction of force due to magnetic field and the direction of magnetic field, and you are asked to calculate what direction the positively charged particle was traveling, you would point your middle finger along the magnetic field and your index finger along the direction of actually your thumb along the direction of force due to the field, and your index finger will be pointing towards the velocity in which positive charge particle was traveling. The same way, this actually applies for any vectors, any two vectors. If you have two vectors, A cross B, you will get a resultant vector C. So the direction of C will always, you can always use this right hand rule to see what direction C is in. So point your hand along A, curl it towards B, and your thumb will show the direction of C. Or, like I said, use your index finger, the first three fingers, and this will be A, that will be B, and so it works for any two vectors, any vector product of any two vectors. So the same rule also applies for force on a charged particle, force on a current carrying wire, or force on a torque on a loop. So if you have a loop and well, yeah, so you have cross product there too, so you can use the formula there. And I can do that problem now. I have motion limit and Faraday's law.
This was when you were young. Or you just fix it.
I just wanted to go through. So
Do we get extra credit for coming?
I don't think so.
Maybe can.
You can try asking. Okay. Sorry? Okay. I am not going to put in explain how it goes. So the first question is, what is the x component of force exerted by infinite wire on segment AD of the loop? So this is the infinite wire, and you calculate the force due to this infinite wire on AD. So what we need to do, what's going on here is, because of this current, there is a magnetic field induced around that wire. And because of the magnetic field induced around that wire and the charge and current going through this loop, you will have a magnetic force being applied on that loop. So what we need to do is, we need to first calculate what is the magnetic field along AD because of this infinite wire, and then using that magnetic field and current path going through DA, you can calculate what's the force. So to calculate the magnetic field on this part of the, at this distance, I can use formula for infinite wire, Ampere's law. I can write I did it previously, so I'm just going to write the value. Yeah, B is mu naught I over 2 pi r, where r in this case is L. That's the distance from the wire to point where we calculate magnetic field. So now that's the magnetic field at all these points. And like I said, my index is pointing along current, and I heard. Were you given some problems with this topic? Do you have this topic for exam?
Yeah. Yeah, I don't, let me see. So
I can
we learned something basic, I think, in class.
I can just make a problem myself. Just um, okay. Also, just to let you know, phi b is the magnetic flux. So the flux has to keep changing for there to be induced voltage, and the formula for flux is well. Let me write formula for flux separately. B dot dA. So if you want to if you want to calculate the EMF induced in a loop, you have to do that. So EMF induced in a loop is basically the rate of change of flux, and flux is the number. It can be taken as the number of magnetic field lines passing through that loop. And as these number of lines keep changing, you will have some EMF induced in that loop. So the way you induce EMF in is by either changing A, which is area of the loop. So you can, let's say, if you have a loop and you can change the dimensions of the loop and induce if there is a constant magnetic field going through that loop, you can just change the dimensions of the loop and induce some EMF and further current through the loop. Or you can change the magnetic field itself, like this case. In this case, you have magnetic lines coming like this. So, so when you get closer, as you get closer, there will be more number of field lines in a smaller area. So magnetic field is increasing. So you can induce EMF by changing field, or you can also change EMF by changing the orientation of magnetic field with the loop. So if I have a loop and there is a magnetic field in this direction, if I have a loop like this, and if I keep changing the angle of the loop, because I have a dot product between B and A, the area vector is pointed this way. It's always pointed perpendicular to the area of the loop, and magnetic field was pointed this way. So as you keep changing the direction, the dot product changes, right? So even if the magnetic field and area are same, you will end up getting changing magnetic flux, which then can be used to calculate the EMF in the loop. This is the, yeah. If you have like any questions in any topic, you can ask me. If you have any part of the code that is not understand. I think that should be all.
Did you have a list of things that were given to you to develop for this topic?
These were the list of topics. These are the list of topics you have for the exam, right? I know what topics you have for the exam. You want to be good at doing circuit problems for resistors and RC circuits, and what was using right hand rule, that's important too. And what was Force on a charged particle, force on a wire, current carrying wire, and torque on a loop. These three are. Let me just go through that formulas. Force on a charged particle is Q V cross B. Force on a current carrying force on a current carrying wire uh, due to magnetic field is IL cross B. Torque is MIA cross B. Do you know all the? What does all these indicate?
Force of the charged particle, the charge times velocity crossed with the magnetic field, right? And force, yeah, third one's force. Second one's force.
Current carrying wire.
Yeah, so I being the current of the wire, the wire crossed with the magnetic field, and tau equals the torque for the number of loops times the current going through the loops times the area, cross-sectional area, whatever. And the cross with the magnetic field.
This is actually the same mechanism that is used to run motors. So you have magnetic field and you have current as they rotate. I think that's all I have.
Okay.
If you have any questions?
I have to do that.
So we let me just point out the direction of magnetic field. Of the loop, the cross-sectional area of the loop is because it's a triangle, I can write it as half BH. We know from Faraday's law that EMF induced in the loop is minus d phi over dt. So phi, where phi is the magnetic flux through the loop. So for this case, we can write phi as dot dA. So calculate when is the EMF induced in the loop maximum, right? So you want to calculate when this value is minimum. For this to be maximum, this has to be minimum, right? So when can that be minimum? We have B and DA, right? Dot product of them. When can a dot product be minimum? What is the minimum value of dot product? B times A, uh, actually integral. Because the area is not changing, or magnetic field is not changing, just the value, the angle between them changing. I can just write this as B times A times cosine theta. So what is the minimum value of cosine theta? So that's the point where you have the minimum phi, right? Okay. Or you want to get the change of minimum in your p phi over t. Okay. Okay. Okay, that part. Like I said, phi b is b a cosine theta, right? The only value changing in this equation is theta. Everything else is constant, right? Only theta is changing.
Right.
So if I take d phi b over dt, that is b times a, and cosine of the, I mean difference of cosine is minus, right? Because theta is a function of time. So this we want to be minimum, right? If you want this to be maximum, this part has to be minimum, which is basically minus ba sine theta, right? So when is that minimum? You want this whole value, which is minus ba sine theta, to be minimum. Yeah, pi over 2. So at pi over 2 we have sine theta to be 1. So we have minus ba, and induced EMF will be minus of minus ba, which is ba. You can also have a minimum minus pi over 2, well here, and you'll get you'll have a maximum value here. For minus pi over 2 you'll have plus ba, and you'll get minus ba, which is basically the same value except you have the direction to be opposite. So EMF induced is, so you'll have current flowing in this direction instead of in this direction. It's the value magnitude is same for both of them, just the direction that was the first part, right? So yeah, when does this happen? When is angle theta pi over 2? We have magnetic field coming out of the loop, and we know that area vector is always pointed perpendicular to the area. So when is pi by 2, pi over 2 theta? At what orientation of this loop does theta between B and A is pi over 2? So if it's going like that, when the loop, so yeah, it's like this. So it's going like this, right? So B is always pointed outwards. A keeps changing the vector direction of A. So when the vector is like that, when the triangle is like this, the angle between them is pi over 2.
Right.
So that's when it is maximum.
It's when the loop's area vector is parallel to the
Actually, this B dot dA,
Yeah.
that's B times A times cosine of angle between the magnetic field and the area vector.
Okay.
So we want theta to be pi over 2 or 3 pi over 2. So at this point, when it is like this, magnetic field is going that way and the area vector is this way, so that's 90 degrees.
Okay.
So
Yeah,
that's when you have
that's
max.
90 from where I thought it was. Okay.
Okay.
That question.
How does the time for max voltage compare to time for maximum magnetic flux through the loop? Oh, okay. So when is there a max in that loop? Like we said, the maximum voltage in that loop is when it is perpendicular to the area vector is perpendicular to magnetic field, right? And when is the when is the magnetic flux maximum in that loop? It's rotating, right? When is it maximum through the loop? Talking about the
Oh, no,
induced.
no, whether the magnetic flux is not when it's 90 or that, or rather, area vector is parallel with the magnetic.
Right, so it's at 0
That
degree.
was the, right, zero.
So that so how do we understand that because we have an understanding of how it looks like. But if you mathematically, we want the magnetic flux, means we want this to be maximum, right? That is maximum when you have theta to be 0. So that is basically this, like this, magnetic field coming out. That's when more magnetic field lines pass through the loop. So you're asked to compare the time for maximum voltage compared to time for maximum flux. So the loop rotates one complete rotation in 2 seconds. So which is 360 degrees. But the time between when the magnetic field is magnetic flux through the loop is maximum to the time when it is the EMF is maximum is a quarter a circle, right? It's 90 degree of rotation, which is 1/4 of the time taken to rotate completely. So you have half a second gap between when the magnetic flux is maximum and when EMF induced in the loop is maximum. That was the second question. Second part. Was there any other question?
I don't know.
I thought you had another.
Pretty sure right, and this one I get. You know, it'd be good if we went over this one too. The last one. Just,
Okay.
and I got the last two, but it took me a while.
You
Yeah.
got
What,
okay. So you are given current and you want to calculate. The first part asks you to just do an integral. So this point. Okay. So you want to go from P to S. P to S to R. So you want to calculate B dot ds from P to S, right?
PR is negligible or zero, right? It's really, it's just the R to S component.
Yeah. Why is it?
Has to do with magnetic field, because you're staying the same distance away from the magnetic field, so you're not changing the magnetic field, the value of
That's
until you go
that's one way of
until you
looking
go
at
along the R.
it. Right. That's correct. That's one way of looking at it. Another way to look at it is ds is an element in the wire, right? And magnetic field is pointed always tangential to the loop. So the dot product. Wait. Oh no, no.
You're moving in the direction of the field, and you're not changing the field.
Yes. ds is that direction. Field is that direction.
So what's DS in this equation?
ds is the element that we're considering. The element of this loop that we're considering.
Okay.
Actually, P to R is not 0. S to R is 0.
Good.
So if you take this, let's call that ds, and the magnetic field at each of those, any part of that is like this, right? So ds is that way if you're going from S to R, or if you're coming from R to S, it's this way. And the magnetic field is that way. And when you take dot product between them, which is cosine of 90, that will be 0. So this is not like electric field. In electric field, we had field lines coming like that outwards, and if you draw a circle around it, any point on that circle will have the same electric field value.
Right.
But in this case, the magnetic field lines will be circular.
Right. So if you move in a circular pattern,
If you move in a circular pattern, you're actually increasing or decreasing the magnetic field.
but
So in an electric, say we have a positive charge particle, if the field is going like that, if you are moving like this radially outwards or inwards, you are changing the electric field, right? But if you are moving perpendicular to the field lines, that is when you have the electric field to be constant. So in this case, if you are moving like this perpendicular to the magnetic field, that's when you don't have any, I mean, ds to be 0.
okay.
So,
So you're saying the SVR component is 0.
Yes.
Sorry,
and you can also use Ampere's law, right? If you have Ampere's law, like you said, if we have that to be 0, the integral, I mean, if you move along the circle and that's 0, we always have u naught times I, right? So that's not 0 when we move along the direction of magnetic field. Now, if we, so for from going if we are going from P to, so we can go from P to R and R to S. Like I said, R to S is 0. So P to R will be, I can change the angle between, not angle, but B is constant everywhere. So I can take B out. and ds is length of this small element, right? Or that arc. I mean integral ds. That's the length of this arc, right? So this is 45 degrees. Or we can also integrate. So here the point r was given to be 0.707, 0.707d. So x and y coordinates are same, so that point is at 45 degree angle to the earth. So when you have 45 degree angle, the length of that arc, I can write it as b times this whole thing will be length of the arc, which is pi over 4 over 2 pi times r. Oh wait, pi over 4 times r. Or we can just integrate. It's not confused. So ds is this small element. I want to integrate that. So the length of that element. There's okay.
It's right, pi over 4r. What you're looking at is 1/8 of pi.
Right. I mean, as long as you understand it, that's okay.
It's 2 pi. Yeah, I get it.
Okay. So 45 degree angle is pi over 4 pi. Or like you said, 1/8 of 2 pi is pi over 4. So b times pi over 4 times the radius r. Or in this case, that's d. Right? Because this was d comma 0. So that is the first part, ds or dl. And
If that's the case, d is the same in p to r, and the magnetic field is also the same in those spots. The magnitude of the magnetic field will be the same at p as it is at r,
yes,
right?
yes,
But it won't be at s
no,
and r. And the field will also be different. So you have a different d value to deal with, different value for magnetic field.
yes.
So it goes back to that, the component that matters is the s to the r.
No, the thing is we're not, no, b, we are not differentiating the value, right? We are
Right.
integrating along the curve.
Right.
So b is not changing, but the dot product of it is changing. And even if b is not changing, we are integrating it, right? It's not.
But you integrate the p to the same value of p and r.
Yes.
So if you integrate p to r, I mean, it doesn't matter if you go p to r or p to s, because you're gonna if you do it all the way through, if you integrate just from p to s, you still get the same answer.
Right.
But I'm just saying, you could just look at the r d s component. That's all. Theoretically, like from a concept point of view.
Uh-huh. If you're talking about integration,
Yeah.
we are integrating length, right? We are integrating the length element, not the radius.
Okay.
So if this was dr instead of dl, because radius is same from this point to that point, there's no difference, and we'll get something minus something.
Right.
Same thing, we'll get 0. But in this case, we are integrating over this length. So as you keep increasing the length, you will have the value of that length. Just to make sure, yeah, that's what dl is. So the second part is if you go from P to R and R to P, you will get this minus the same thing, because dot product b dot ds, you will have positive for one case and negative for another case, right? So for this case, the magnetic field due to the current, wait, yeah, it's going this way. So actually this is negative, because the angle between them is 180, right? Cosine of 180 is minus 1. So for this case, you have a negative. If you are going from R to B, that is along the curve, and the magnetic field is also along the curve. So you have cosine of 0, and you will get P times pi over 4 times D. And you can add these two and that will be 0. Or you can also use Ampere's law. Just integrate from, you're basically integrating from that point to that point, right? It's the same point. You're not changing anything. So you'll get that will be 0. Even. I understand why you're getting confused. I mean, it's just that because we have that's magnetic field, and it's sometimes you get confused with electric field. It's in electric field, if you go around the loop and you do integral E dot dAl, you'll have perpendicular components. So every point is at 0. But in this case, you're going along the magnetic.
I think I get it. Oh, is this on?
Yeah, I think it's. Did you write it? Okay.